Welcome to Math 2320. This is section 7.5. The main focus here is the Dirac delta function or the impulse function. It's a little strange when you first see this, so let's talk about this thing slowly. The way that the Dirac delta function works is it's considered an impulse. It's an impulse at a particular t0 where it's been shifted. Outside of t0, the function is 0. At t0, the function goes to infinity. So think about it as a spike at t0 that just goes up forever, but this thing actually seems to have 0 width. The other thing strange about this particular function is if you integrate it from 0 to infinity and you're integrating across this t0, the area under the curve is exactly 1. Now that seems to defy logic a little bit because it has no width but yet infinite height. The way you go about defining it, there are two ways. One is you can define it first as a little box right around t0, and with the box you maintain that this area under the curve is 1. And then you have a limiting process where the width of the box decreases and yet the height goes up, but yet maintaining an area of 1. And then you keep doing that. Shrink it even further, but the height goes higher. So in the limiting process, the width goes to 0, but it spikes up to infinity. Another way to do this is to define it as a triangle, where again you maintain the width and the height in such a way that the area is 1, but yet you shrink it in terms of width while the spike goes higher and higher. So this is your impulse function. Has no width, but yet it runs off to infinity. And so we have our differential equation here, where we have a first order problem. Our driving function is an impulse at t equals 4. Initial condition is y of 0 is 0. So we use Laplace transforms. We take the Laplace transform of both sides. So fairly standard here on the left, Laplace transform of y prime. We have s, Laplace transform of y, minus y at 0. Well, y at 0 is 0. And on the right hand side, we have the Laplace transform of this impulse function. Well, the Laplace transform of the impulse function at t0 is e to the minus s exactly at t0. So in our case, this is e to the minus 4s. Alright, so we clean things up. I call the Laplace transform of y a, group things together. Alright, and then we divide by s minus 3. And so here is the thing that we need the inverse Laplace transform of. Well, looking at this, I recognize that this looks like the Laplace transform of f of t minus a u t minus a, because it's of the format e to the minus as multiplied by a Laplace transform. And so in our case, from the e to the minus 4s, we get a u t minus 4. from the 1 over s minus 3, that would be e to the 3t, but it's delayed by this t minus a, in our case t minus 4, and that's our solution to our differential equation. Now, what does that look like? Well, what it looks like is the following situation from Wolfram alpha. The function initially at y0 is 0. So this starts off at 0, is 0. So if you consider over here is 0, the function stays 0 all the way out until we get here to 4, at which time it has the impulse and then it runs off to infinity. Another way of calling the unit step function in Wolfram alpha, so our u of t, you'll sometimes see as h of t, where this is the Heaviside step function. So just a little look to see what exactly would this thing look like as our solution to our differential equation. Alright, in question 2 here, same situation, except now we have a second order problem. The impulse is at t minus 4 pi, so shifted over our two initial conditions. So take the Laplace transform of both sides. My initial condition, y at 0 is 0, y prime at 0 is 1. Alright, so let's clean up and get together all the stuff with the Laplace transform of y. So here I have an a part, another a part. So group that together. Alright, I'm going to take this minus 1, move it to the right, and now divide through by s squared plus 1. Alright, so I recognize this is the inverse Laplace transform for the sine of t. Here is our delayed u of t minus 4 pi, and it's the sine, again being delayed. Well, can we clean that up a little bit? What about this sine of t minus 4 pi? We'll use your sine for the sum and difference of two angles and split it up. Sine t cosine 4 pi minus sine 4 pi cosine t. Well, the cosine of 4 pi is 1, sine of 4 pi is 0, so all that's missing. And so sine of t minus 4 pi is really the sine of t. And so we get our solution for this second order differential equation. Question 3, we have a beam. We have a beam of length L. This is represented along the x-axis. Y of t is its vertical deflection. We're going to put a concentrated load right here in the middle at L over 2, and the load is W0. So, what happens? We model this as a fourth order differential equation. Alright, and we're trying to see what does y look like along the length 0 to L. Alright, well, fourth order, we need 4 boundary conditions. Y at 0 is 0. Y prime at 0 is 0. Y double prime at L is 0. And Y triple prime at L is also 0. So it's attached here at this wall. the other end is free. All right, so we have some difficulties here though. Now the difficulties are that we are given the initial conditions for y double prime and y triple prime not at 0 but at L. So that does create some headaches. Alright, so the Laplace transform of my fourth order y triple fourth prime. So s to the fourth Laplace transform of y minus s cubed y at 0 minus s squared y prime at 0 minus sy double prime at 0 and finally minus y triple prime at 0. Now you say, well, wait a minute, we didn't get y double prime and triple prime at 0. No, we did not. So, but we do know that y at 0 and y prime at 0 are both 0. So I'm going to have to let these in the situation, in the problem, as unknown constants for now. Alright, so the Laplace transform of the left and the right, we get this situation, E and I were constants. Alright, so at that point we start isolating for the Laplace transform of y. Alright, I'm going to divide through by EI. Now I'm going to start getting this A S fourth alone. Alright, so I'm moving my y double prime at 0 and triple prime at 0 to the right. And now I'm going to multiply by 1 over s to the fourth power. It'll cancel this s, giving me s cubed. I've got a s to the fourth, another s to the fourth on this term. Alright, so let's see. We're going to need some basic facts. The Laplace transform of t to a power was n factorial over s to the n plus 1. Alright, so let's see, this 1 over s cubed, I needed 2 on the top, so put a 1/2 in the front. For this term, the s to the fourth, I need a 6 because I need a 3 factorial, so a 1/6 here. And similarly on this term, I'm going to need a 6. Alright, so for this piece, this is 1/2, my constant in the front. This goes back to x squared. Y double prime at 0 still sits there as a constant. This one is x cubed. Alright, so this went to there. This went to here. And the inverse Laplace transform of this term has this piece in it, so this piece is delayed by the delay, so x minus 1/2 L cubed. So there's our solution, and we'd be done if we knew y double prime and y triple prime at 0. Alright, so what do I need to do? I need to take our solution, differentiate it once, twice, 3 times. Alright, and see what do we have. Now this delayed function, this u x minus 1/2 L, remember, is 0 up until L over 2, and then is 1 thereafter. Ours is modified by this. Alright, so what do we know? We know that my solution at L, the triple prime at L is 0 and the double prime at L is 0. All right, so that's going to be y triple prime plus this piece. Now, where did that come from? If I plug in L, this is L minus a half L, giving me 1/2 L, and there the function is 1 times that term. And so I solve, I figure out what y triple prime at 0 must be. We do the same thing for y double prime at L. All right, putting in what we know, and we get the solution for y double prime at 0. All right, and finally, when we plug everything back in, we get our solution over our range of x from 0 up to L for this fourth order problem.